so today we'll be talking about energy and matter. Energy is the capacity to do work. So energy is measured in calories, which is the amount of energy needed to raise the temperature of 1 gram of water to 1 degree Celsius. Calories are also measured in joules, which is 1 cal equals 4.184 joules. So when we eat food, proteins, carbohydrates, and fats metabolize to form small molecules that are in turn used to prepare new molecules that cells need for growth and maintenance. So food is measured in a nutritional calorie. 1 calorie equals 1 kcal, and 1 calorie equals 1,000 calories. So the 1,000 calories are what we really see when we're looking at calories, but then on food nutrition labels, it's labeled as 1 cal. So really we're having 1,000 calories, but it's just labeled as 1. So the caloric values of different foods are the predicted amounts of energy, and metabolism, the rate at which your body burns the energy. So in protein, there's 4 calories per gram. Carbohydrates, there's 4 calories per gram also, and fat, 9 calories per gram. So why don't we go look at some foods and measure out how many calories are in them. So hot fries. In hot fries, there's 4 grams of fat, 20 grams of carbs, and 2 grams of protein. So let's see how many calories are in hot fries. So, 4 grams of fat, protein, 2 grams, and carbs, 20. So, the conversion factors for fat is 9 calories per gram. So, we have 4 grams, and we have 9 calories per 1 gram. So, grams cross out, and it's 36 calories in just fat. So now let's do protein. So there's 2 grams of protein, and the conversion is 4 calories per 1 gram. Grams cross out again, and that's 8 calories. And the same thing for carbs. 20 grams of carbs, 4 calories per gram. Grams cross out, we have 80 calories. So each, the fat, the protein, and the carbs make up the calories for the hot fries. So the total that we come up with, 6 plus 8 plus 8, would be 124. So there's 124 calories in hot fries, which is about 130, which is on the bag. Now let's look at the Nature Valley Crunch Bars. So the serving size for these is the 2 bars inside the 1 package, and there is 7 grams of fat, 28 carbs, and 5 grams of protein. So let's look at the caloric value for the Nature Valley granola bars. Seven grams, carbs, 28 grams, and protein, 5 grams. So once again, with fat, there's 9 calories per gram. Grams cancel out, and that is 63 calories. And then with the carbs, there's 4 calories per gram. Grams cancel out, 112 calories. Protein, 4 calories per gram. Grams cancel out, 20 calories. And let's add that up. Ends up being 195. And on the box, it's 190. So just about right. So now for a quick change. There's 3 states of matter. We have solid, liquid, and gas. So in the solid, such as ice, Particles are close together and are highly organized and attractive forces. Here's an example of the solid, the molecular structure. In the liquid, particles are much closer together, they're disorganized, and they exert force of attraction. Here is a molecular diagram of the liquid. So an example, water. Gases are particles far apart, they move rapidly and independently. An example of that is carbon dioxide. Here's a gas, they're freely moving and independent. So that's it, now I'll have Chris talk to you.
Hey, what's up? Come on in, we're just doing some fun chemistry experiments today. So, today we're going to be going over different types of reactions and how energy works. And you have two different reactions with energy. You have endothermic and exothermic. And as you can see, an endothermic reaction absorbs energy. So an example would be ice going to liquid water. And the particles in the solid ice, as you can see, are very densely, tightly packed. And when it goes to liquid water, I can't talk, they open up and they become a little more disorganized. Versus an exothermic reaction releases energy. And an example is going from liquid water to ice, where the particles then become very densely compact. So you can have different types of reactions. You can have solid to a liquid, which is known as melting. Happens a lot in winter. And it's basically the opposite of freezing. So the solid goes to a liquid, the particles get looser. And we can actually do a demonstration of this over here. What we're going to do is we're going to take some of the Chartwell's ice and we are going to put it in a bowl. And the heat of the room is going to melt that ice. And what we're also going to do is ice can also melt in a liquid. So Professor Collins, if you would love to explain this concept to us one day, that would be awesome. It's a color changing cup. We're going to put some room temperature water into a cup and we're going to throw some ice into it. And when the ice melts, in both of these cases, it's going to be considered an endothermic reaction. And when it melts in the cup, it's eventually going to turn the cup to a dark purple pinkish color, which you might be able to see because the ice is touching the walls, but by the end of the video, it's going to be completely purple. And then we're going to go back over to the lovely window. Another type of step you can have is a liquid to a gas, which is called vaporization, which is the opposite of condensation. And it's an endothermic reaction as well because it absorbs energy. And you can see the liquid water turns into steam. And we're actually going to try that in an experiment. So the disorganized gas molecules are very few and far apart, whereas the liquid water is more closely together. So we're going to do a demonstration of this over here. We're just going to take your standard coffee cup and it's filled with a bunch of water, room temperature, and we're going to throw a plate over it. And we're going to microwave it. And basically what's going to happen is when we lift the plate up, steam is going to be released up, which is known as vaporization. And what's left on the plate is going to be condensation, where the water is actually touching the plate. So we're going to let this go for about 2 minutes, and we'll come back to that. Okay. And we're headed back over here. And the last type of reaction we have, which is very, very rare, is called solid to gas. And it completely skips the liquid phase altogether. It's very rare, like I said. The only example that I know of is going from dry ice, which is solid CO2, to a gaseous, I probably pronounced that wrong, CO2. And it completely skips the liquid phase. And unfortunately, I do not have any dry ice, and I'm not sure if it's legal to have dry ice or not in a dorm, so we're not going to be able to perform that experiment today. But it would be very interesting. So we're going to move on over this way, and now I'm going to talk to you about heating curves and cooling curves. So it has a lot to do with what we just covered. And as you see, the heating curves, what we're going to go over first, as temperature rises, heat is added. So you start off with a solid that has very densely packed molecules, and eventually it gets to that melting point. So it varies for each different compound or element. And once it gets to the melting point, it's going to stay at that constant temperature. But then we can take it from a liquid and we can make it boil, which is going to raise up even more. And going from a solid to a liquid, the particles are going to spread out and become very disorganized, but they can become even more disorganized once it reaches a boiling point, which is going to turn that liquid into a gas, which is what we're going to see in a few minutes with the microwave, in 22 seconds. You can also have a cooling curve, which is basically the opposite of a heating curve. Once you get to the very top, it's kind of like the economic scale. Once your stock goes all the way up, eventually it's going to crash, because that's how America works. And when it starts to crash, we're going to go from a gas to a liquid. So basically we're going to be removing the heat as the temperature is decreasing, and this is all going to happen. So the gas is going to start to form more particles again, it's going to turn into a liquid, and then that liquid is going to freeze and go into a solid, for example, water. So we can check on our cup in the microwave because it's all set. If you want to come in here. And when we lift this up, steam is going to be released. It's kind of hard to see. As you can notice on the cup, on the side of the cup, that's called condensation, where there's a ton of water molecules just randomly placed there because the steam was cooling down on the cup and it turned it back into water. And now we can go back to our original experiment over here. And as you can see, we had placed a solid object into a bowl, and it's not very warm in here, so we haven't created much water, but you can see there's a little bit of water in the bottom of the bowl, and that's an example of an endothermic reaction because it's absorbing energy. And also, we have melted some ice in a cup, which you can see the water has absorbed that energy, and now the cup has gone purple because when there's a cold liquid in here, it turns purple. And you can see the amount of ice in the cup here has almost dissolved all the way. And that's pretty much how energy works, how heating and cooling curves work, how solids can go from a liquid to a gas, and they can even skip stages altogether. So thank you for listening, and now we're going to have Kat talk to you. Have a great day.
From the disruption of the construction to the camaraderie of the football team, this is Worcester State News, the greatest college campus news source. Today, we're going to be talking about what's all the rage around the college community: chemistry. There are three common intermolecular forces that play a key role in bonding. We have London dispersion, dipole-dipole interaction, and hydrogen bonding. The size of the molecule determines the strength of these bonds, but it also determines the melting and boiling points of these molecules, as well as their state of matter. London dispersion forces can result from momentary changes in electron density. However, these are very weak, but these result in temporary dipoles, which can make other weak temporary dipoles in other molecules. So it's pretty great. This here is a diagram that depicts a temporary dipole. Here we have our gelatinous molecule. However, we have more negative particles here, positive particles down here, which makes a temporary dipole that is vertical, whereas more negative up here and positive down here. However, with momentary shifts in the molecule, this dipole can be shifted as well, where the negative particles are on this side of the molecule, and the positive is on this side of the molecule, which results in a horizontal dipole. Here are the weakest of all of the intermolecular forces. But next we have dipole-dipole interaction, the next strongest on the list. These are accurately depicted here, where we have two dipoles interacting with each other amidst this box. We have two water molecules here, and these have two horizontal dipoles right here, positive, negative, which has not been drawn, but should be, positive, negative. But the positive and the negative dipoles attract. These two dipoles here result in an interaction. It's good stuff. Third and final bond that can be classified as an intermolecular force is a hydrogen bond, where a hydrogen bond to a highly electronegative atom, such as oxygen, nitrogen, or fluorine, attracts to another oxygen, nitrogen, or fluorine of another molecule. Here we have two molecules, NH2 and NH2, where the hydrogen is bonded to a nitrogen, but is also electrostatically bonded to another nitrogen. These were not drawn to scale. And this bond is a hydrogen bond, and it is the strongest of all the intermolecular forces. These hydrogen bonds also have a key role in biological molecules such as DNA and RNA. This wraps up this segment of WSU News. Tune in next time to talk more about boiling and melting points in specific heat. Thanks for joining us. From the disruption of the construction to the commodity of the football team, this is Worcester State News, the greatest college campus news source. During this session, we're going to be talking about everything that is all the rage, specific heat. It's a pretty hot topic. Specific heat is the amount of heat energy that's needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. It can be calculated using this equation. The heat energy over the mass of the substance times the change in temperature, which equals calories or joules over grams times degrees Celsius. The larger the specific heat, the less temperature will change when absorbing heat energy. Water has a higher specific heat compared to other liquids due to its strong intermolecular forces. It takes much more heat energy to break those bonds within the molecule than breaking the bonds of other substances. Also, since the amount of heat absorbed equals the amount of heat released when cooled, water can release a great amount of heat energy when cooled by just a few degrees. This has been specific heat. If you look to your right, you'll see the great football field.